In my last video, we looked at dividing polynomials. An example might be dividing a quadratic expression by a linear expression. So we could have had 6x squared plus 2x minus 3 divided by x plus 4. In this video, we're going to look at the factor and remainder theorem. Let's start off with the remainder theorem. What I want to do is give a formal definition and then work through some basic examples. So the formal definition of the remainder theorem is if we divide a polynomial by x minus a, the remainder is given by the f of a. Let's write that down. We can state that the f of a is equal to r, where r is the remainder. So what does this mean? What I'm going to do is take now a function of x, and this is going to be some polynomial. Let's say that was x squared plus 5x minus 4, or 3x cubed plus 8x minus 8. I'm now going to divide that by x minus a. When we do this, we're going to get a new function of x, which I'll define to be the g of x, plus some remainder. And that remainder will be given as r over x minus a. At this stage, I'm going to multiply through by x minus a. We have the f of x will be equal to the g of x multiplied by x minus a. And then we will have now r. The x minus a's are going to cancel. So we can say now that the f of a is going to be, and subbing this in, we're going to have the g of a, and then we're going to have 0, plus now r. This is going to give me 0, therefore we can state the f of a is equal to r. And this gives us our formal definition of the remainder theorem. If we divide a polynomial by x minus a, the remainder is given by the f of a. If you want a numeric equivalent just here, let's just think what this would look like. If we take 7 over 2, that's going to be divided, and that will give me 3 as the integer quantity, and then 1/2 as the remainder. So if you want to link these two, that's a nice numeric equivalent. So this looks quite overwhelming. In all reality, the examples that we're going to do show that this is a fairly straightforward topic. I've only included this definition for completeness. What we're going to do is take a basic quadratic now and look at the value of the remainder when we divide it by a linear factor. So what I'm going to have is x squared minus 2x plus 4. And I want to find the remainder when this is divided by x minus 2. What I'm going to do is define a function of x, and that function of x is going to be x squared minus 2x plus 4. If we just look up here, when I now have the f of a, this gives me a remainder. So what I'm going to do then is state that the f of 2 will be equal to my remainder. What we're doing, we're evaluating now the f of 2. If that was plus 2, we would do minus 2. If that was minus 5, we would do the f of 5. If it was plus 6, we would do the f of minus 6. What we want to do then is find the remainder. So let's do the f of 2. Well, the f of 2 is going to be 2 squared, which is 4, minus 2 lots of 2, which is minus 4, plus 4. We can see that the f of 2 is going to be equal to 4. Therefore, I can state now the remainder when we have x squared minus 2x plus 4 divided by x minus 2, the remainder is going to be 4. That is all we need to do. So while the definition is quite theory heavy, the actual application and process is fairly straightforward. We're just evaluating now the f of a to give us now the remainder. We plug this into the function and we find now the remainder and simply write it down. Let's go ahead and look at another example. So let's take a cubic this time, 2x cubed minus, then we'll go for minus x squared plus 3, and we want to find the remainder when this cubic is divided by 2x minus 1. In this particular case, I have the form ax minus b. So what we need to do here is the f of b over a to give us now our remainder. So when I have a coefficient on the x term, I could write that as ax minus b, and I'd simply go ahead and evaluate the f of b over a. So let's define our function. Let's say the f of x is going to be 2x cubed minus x squared plus 3. So we can say that the remainder will be now when we evaluate f of 1/2. So all I've taken now is simply the factor here and said to myself, well, if this is of the form ax minus b, I want now b over a, and that's what I've done. So if that was 5x minus 3, we would do the f of 3 over 5. If that was 7x plus 2, we would do the f of minus 2 over 7. Okay, let's go ahead and do that. That will give us now our remainder. So subbing this in, f of 1/2, well that's going to be 2 lots of 1/2 cubed, which is 1/8, minus now 1/2 squared, which is 1/4, plus 3. So what do we end up with? The f of 1/2, that's 1/4, minus 1/4, plus 3, we end up just with 3. So what we can state then is when 2x cubed minus x squared plus 3 is divided by 2x minus 1, the remainder is going to be equal to 3. So we'll have now a remainder, and that's going to be, now remainder is 3. So nice and straightforward. So this might have been slightly off-putting. I included it for completeness as a definition to the remainder theorem. This is all we're doing. We're simply stating now that f of a is going to be equal to r. So if we had now, let's say, a linear factor of 3x plus 5, we could state now the f of minus 5 over 3 would give us our remainder. So all we're doing is simply writing this now as b over a when we've got this particular form here. Okay, let's do another example. Now in this one we'll take a cubic function. So let's go ahead and get another cubic function, and we'll have 3x cubed plus ax, where a is a constant, and then we'll subtract 1. Now we might be told that this has a remainder, and I'll just jot this down. So remainder of 4 when divided by, and let's give this a linear function, a linear factor, when divided by, and I'll just jot this down, let's go for x minus 1. We need to find now the constant a. So find the value of a. So what we've got then is this cubic. We've got a cubic in x. We've got now a constant, which is a. We're told the remainder is 4 when it's divided by x minus 1, and we need to find the value of the constant a. So let's write this now, and we'll define the function of x to be now 3x cubed plus ax minus 1. So all I've done is let the f of x be equal now to our cubic expression here. So what I can state now is that the f of 1 will be equal to 4. Let's take a moment to think what I've just put. We know that the f of a will be equal to r. This gives us our remainder. So all I've done is subbed it in. If I do the f of 1, I should get 4. So let's go ahead and do that. The f of 1 is going to be now 3 lots of 1 plus a lots of 1 minus 1. So that's going to give me 4. So we get 3 plus a minus 1. So we get 2 plus a is equal to 4. So we can see that a is equal to 2. So we found the value of the constant a by simply using what we know about the remainder theorem. Let's now move on and look at the factor theorem. If we divide a polynomial by x minus a and the remainder is 0, we can say that x minus a is a factor of that polynomial. So this is a special case of the remainder theorem. So if we do the f of a and it's 0, then we can say that x minus a is a factor. So for example, now if I looked and I had the 2x minus 1, if I now said that I was dividing some polynomial by 2x minus 1 and I did the f of 1/2 and this was equal to 0, I could say now that this right here was going to be a factor, and that gives us the definition of the factor theorem. So we can say the f of a is equal to 0, therefore we can say x minus a is a factor. So this is going to come in really quite good use when we look at higher order polynomials. So for example, if we're solving cubic equations, this will allow us to find a and then go ahead and solve. In a later video, we're going to spend more time solving cubic equations using the factor theorem. In this video, we're just going to look at a brief application of it. But essentially, that's our definition. So let's put this into action. What I'm going to do is just take a quadratic. So if we just have some quadratic, let's say we'll go for x squared minus x minus 6. So what I can do, let's just define this now. So we could let f of x be equal to this. So if I wanted to factor this, now what are we going to have? We're going to have x minus 3, and then we're going to have x plus 2. Therefore, it would be fair to say that if I evaluated the f of 3, I'm going to get 0. That would tell me now that x minus 3 is a factor. If I evaluated the f of minus 2, that should also give me 0, as these are factors. So if we did that, let's see what we would get. Let's do the f of 3. So the f of 3 is going to be 3 squared, which is 9, minus 3 minus 6. And that gives me now the f of 3 is equal to 0. Therefore, we can say that x minus 3 is a factor now of this quadratic. If we do now f of minus 2, well, that's going to be 4 minus 2, which is plus 2, minus 6. We can say the f of minus 2 is equal to 0. We knew that anyway, as we can factor this. So let's say we had a quadratic equation x squared minus x minus 6 is equal to 0. We can say now on this, if x minus a is a factor to this expression right here, then x is equal to a is a solution. So we can state if x minus a is a factor, and just jotting this down, to the equation above, then we'll write this here, x is equal to a is a solution. And this is what we're going to use on our cubic equations later on. So just jotting that down. So we know that's the case anyway, because we've solved lots of quadratics in the past. Okay, so let's have a go with this and work through an example. If we think about a cubic equation, in the past we've been able to solve cubic equations if we've had now a common factor of x right the way through. So if we had, for example, x cubed plus 3x squared minus 10x is equal to 0, x is common. We can take that out. We got x squared plus 3x minus 10 is equal to 0. We've got a linear multiplied by a quadratic. The quadratic will factor again. We'll have x plus 5 and then x minus 2. So we can see our solutions. We could have x is equal to minus 5, x is equal to 0, or x is equal to 2. This won't always be the case. Sometimes we'll have a constant. So for example, this might have just been minus 10 instead of minus 10x. In the next video, we're going to look at solving cubic equations using the factor theorem. In this particular video, I just want to look at an example and then factor a cubic expression after we've been told one of the factors. Sometimes you'll have to go and hunt them yourselves, but for now we'll just look at one where we're given a factor. We might be asked, let's do one. Let's say we need to show that x minus 2, and we'll put this here, is a factor, so just jotting this down, is a factor of, now, and let's take a cubic. Let's go for x cubed, so let's go for x cubed minus 6x squared. We'll go for plus 11x and minus 6. So we need to show that is a factor, and then the question might say, and hence fully factor, okay, and hence fully factor. So let's go ahead and look what we've got. Now, the first statement I'm going to make now is the following. If x minus 2 is a factor, so it is a factor, then we can say that the f of 2 will be equal to 0. That's the statement I'm going to make. I'm going to evaluate the f of 2, hope it equals 0, and we can state that it's a factor. So show that. I'm just plugging in 2. If that was now, let's do some more. Let's say we had 3x plus 7, and we wanted to show that now was a factor. We'd have to do f of minus 7 over 3, and we'd hope that that would be equal to 0. If we had 5x minus 1, we would do now the f of positive 1/5. And again, to be a factor, when we evaluate 1/5, we get 0. If we had now x plus 4, we would simply go ahead and do the f of minus 4 to give us 0 if these were factors. So we can say if factors, so let's put that there, if factors, then, and then these statements right here. So let's do that. Let's now define this cubic to be the f of x. So we can just write here, let f of x be the cubic x cubed minus 6x squared plus 11x minus 6. So we can state now the f of 2 will be equal to 0 if now x minus 2 is a factor. You should be able to get away just now with writing f of 2 equals 0. So let's do that, f of 2. Well, f of 2 is going to be 2 cubed, that's 8. Minus 6 lots of 2 squared, that's 24. Plus now 22 minus 6. So what do we have? We have the f of 2 is going to be now 30 minus 30, that's 0. Therefore, it's a factor. If it had been any other value, then it wouldn't. We simply would have had a remainder. In some exams, and do check with your teacher or your exam board, they will expect you to show full working. So on that second term, minus 6 lots of 4, and then tidy up as you go. So we know now that x minus 2 is a factor. We need to fully factor this. We got a couple of choices. We could choose polynomial long division, as we saw in the last video, or we could just equate coefficients. So I could write that x minus 2 multiplied by some quadratic ax squared plus bx plus c, and we can set the identity now. This will be equal to x cubed, so let's write it here, x cubed minus 6x squared plus 11x minus 6. So let's check that I've got all of that in, and we'll just put this in here. That looks pretty good. Okay, so with this one I'm just going to equate coefficients. In the last video we saw how to do this, and I'm going to go through it fairly quickly. So on the left hand side we're going to have now the cubic terms. That's simply going to be a. That's the only thing that I'm going to get in terms of x cubed. On the right hand side we've just got one of those. I'm now going to look at terms in x squared. On now the left hand side I've got b minus 2a. So bx squared minus 2ax squared. So I write b minus 2a. And then on the right hand side I've got x squared, and that's going to give me minus 6. I don't need to find the terms in x, as I can just use the constant. I'm going to have enough information to do that. So if we look at the constant, on the left minus 2c, and on the right minus 6. So at this stage we can go ahead now and find the values of a, b and c. And as stated, you can find this any way you want. So a is going to be equal to 1. If a is going to be equal to 1, we can sub it into here, and b is going to be equal to minus 4. And then this one right here, minus 2c is equal to minus 6, so c will be equal to 3. So what we have then is x minus 2, and then we have now a, which is 1, so we have x squared minus bx, so minus 4x, plus c, and that's going to give us now a quadratic expression. For quadratic factors, so x minus 2, and then we'll have x minus 3, and then x minus 1. So if you've done any graphing with cubic equations, let's go ahead and do that. We could go ahead and get now an accurate, a sketch anyway, of what this would look like. So we're going to have now a solution. If we set this equal to 0, let's set this equal to 0. So we're going to have now 1 here, we're going to have 1 here, and we're going to have 1 here. So this would be 1, 0, 2, 0, 3, 0. It's going to cross the y-axis when x is equal to 0, so that's going to give me now this point right here, which is going to be 0, minus 6. So drawing the cubic, we'd come round, we'd come up, and then we'd do something like that. So you can see that we can use this factor theorem to go ahead and solve for cubic equations. And in later videos we will look at that. So that's a nice application now to show that this is a factor, and then we can go ahead and use a method of our choice to fully factor. You might have used polynomial long division, you might have just equated coefficients. Okay, let's move on. We'll do one last example, and let's just take another function. Let's say we've got x squared, so we'll take x squared plus ax, where a is a constant, plus b, and again b is a constant. We might be given information. We might be told that when x squared plus ax plus b is divided by, and I'll just write here, divided by x, and we'll go for x minus 2, we might be told that the remainder is equal to 4. And also we might be told that x plus 1 is a factor. So x plus 1 is a factor, and we would be asked now to find the values of the constants a and b. So find a and b. Okay, let's take this. What I want to do is make two statements. I'm going to have the f of x is equal to x squared plus ax plus b. Let's look at this first statement. When it's divided by x minus 2, the remainder is 4. So I can state that the f of 2 is equal to 4. If I divide by x plus 1, I get 0. This is a factor. So what we can say then is the f of minus 1 will be equal to 0 if it's a factor. So all I'm going to do is work off these two things and set up a simultaneous equation. So let's do the f of 2. Well, the f of 2 is going to be 2 squared, which is going to be 4. Then we're going to get plus 2a plus b. that now is going to be equal to 4. So 4 is equal to 4 plus 2a plus b. So we can see from here now that we could write this now. The 4's are going to cancel. We could say that b is equal to minus 2a if we liked. And we'll call this one equation 1. Let's now look at the f of minus 1. If we do the f of minus 1, that will give me 1 minus a plus b. We know that this is going to be equal to 0. So we can say 0 is equal to 1. Then we're going to have now minus a, and then we're going to have plus b. So we'll call this one now equation 2. So if we now sub this in, b is equal to minus 2a. So what we'll have then is the following. We'll have equation 2. We'll have 0 is equal to 1 minus a minus 2a. So what does that give us now? A is going to be equal to 1/3. Let's just check that. A is going to be equal to 1/3. So all I've done is gone ahead. I've got 3a. 3a will be equal to 1. Okay, so let's now look if we sub this back into either one of these. We can find b. Therefore, we can state that 0 will be equal to 1. We've got now minus 1/3. So minus 1/3 plus b. So what's that going to give us? b is going to be equal to minus 2/3. Let's go ahead and check that they work. So we're going to have now 1 minus 1/3 minus 2/3. That's going to give me 0. It works in that one. And we can see on this one now that if I sub this in, we're going to end up with those values. So there we go. We've used the factor theorem here, the remainder theorem here, and simply solved the simultaneous equations for the constants a and b. So that's a brief introduction and some basic examples now to both the factor and remainder theorem. In later videos we'll look at cubic equations and solving those, and also go on to a range of exam style questions that are often quite similar to these. I appreciate the first part of the video was quite overwhelming and to some extent unnecessary. As long as we have some understanding of evaluating the f of a and either having it set to some constant or 0 if we're using the factor theorem, that's generally adequate to make your way through the vast majority of questions.